Oh, okay. So here we have some nice constructions. Um, we have to kind of identify the structure and construction that we use to sketch it and then name it. So I think for this one, actually, I'm going to switch away from my iPad. I'm going to go to this guy. So let's actually use some Smart Notebook action for this. This isn't going to be perfect, but it should work. Where are we? There we are. Okay. So I'll try to do the construction. What just happened there? Oh, there it goes. Okay. I'll try to do the construction kind of using my tools that I have built in. But it's going to be a little bit crude because I'm going to be using my touchpad here and my mouse instead of anything else. So please bear with me. Again, I'm not going to cover the brief explanation of why it's going to work. At least I'm not going to write it out. I'm probably not even going to write out this because I'm going to be, again, typing and kind of using my mouse. But I'll talk through them. So like if you're kind of falling into what's going on, um, you should be able to glean pretty much what's going on. Let me zoom in a little closer here. Okay. So let's talk about this. So if I want a line parallel through P, again, it kind of goes back, if you watch the last video, especially towards the end, it goes all the way back to finding something that is already parallel. So like me as a person, even a geometry teacher, can't force things to be parallel. What I'm looking for is something that I already know is parallel to bring in as a fact, to bring in as a module, to bring in as that friend that's going to do the work for me. So let's get to it. If I want parallel, hopefully the first thing that strikes into your mind is an isosceles trapezoid. And I think I have a picture of one right here that might help a little bit. Okay, here we go. So if you kind of consider an isosceles trapezoid, the reason we want to bring this guy in is because we already know for a fact that we have parallel lines top and bottom. So it's not me trying to create like a whole new method over here or any kind of crazy idea. I already know these are parallel, so if I can turn this diagram into an isosceles trapezoid, then I have to be able to have parallel. So it goes back all the way back to a point analysis because in the end, this has always been about picking the right points. And same is true here. So like if I'm going to construct an isosceles trapezoid, what it really amounts to doing is making sure I'm picking out 4 points really, really well, but making sure I'm picking them out on this diagram. Now in the end, I'm going to use circles and arcs and stuff to build it, but it's still about picking the right points in the right places. So if I'm going to take this diagram and make an isosceles trapezoid, because I know isosceles trapezoids have parallel lines, I need 4 points. Well, I already have 1 point for me right here at P, so I don't have to do anything there. In fact, let me change my color. Let's go red. So I already have 1 point here, P, bam. So I don't have to do anything with that. That's kind of like this point right here. So that's here. Now, the bottom two, I would argue, don't really matter as far as like where I put them. They just have to be somewhere on the line. Like it doesn't matter if they're spaced out really far or really close. They just have to be there. So I'm just going to put them here and here. So now the fun comes in when I need to pick this fourth point, which I'm going to kind of color light blue. I know it's got to be somewhere probably around here-ish, but I don't want to guess. This method's super precise. It doesn't use measurement. It uses logic and fact. So I don't want to start going into like I think it's about right here kind of arguments. That's terrible. Instead, I want to understand that if I need to fix a point um, in space, I'm going to need two distances to do it. Now, the reason why this is parallel is because this does use two distances when trying to fix points. Let's go here. Okay. So like if you take this red point right here, it's fixed by two distances, by this guy and at the same time the other one from the base. Okay. So if I'm talking about this point, this circle right here, centered at the bottom left corner, defines this distance as its radius. At the same time, this bigger circle, using this as its center, defines this distance as its radius. So that's why this works, because in the end, same has to be true for this light tan point. And so like if this distance to the top left is taken from like the opposite point, and then this distance is taken from ooh, come here guy, is taken from the opposite point, those should intersect right where the other point is located. And that's ultimately how this works and what you're about to see on the left. So if I want to fix this new teal point over here, I have to use the same distances as I used from P. So let's go line color red. Okay. So in other words, this distance that I have from my leftmost point and this is if I was using a compass, so I'd actually need a circle. I'm going to take the same distance, but I'm going to center it over here. So I know at this point, this new value, or this new, there it is, okay. So this point I want has to be somewhere on this circle. Now, obviously, it's probably going to be kind of in this region, but that's kind of why you need two circles, though. Like, because if I just said it's this distance away from the line, I could pick anywhere on this line that would fit. But that's not what's going on at all. Instead, I need to involve a second distance. Let's color this one in light blue. Okay, taken from the opposite point out to P. Because this purple and this red line fix P, those same two distances have to fix my point that I'm looking for. So I'm going to take that same distance, but I'm not going to use it here. I'll center it over this circle instead, right there. And again, where those cross, just like over here, purple and red cross to find this point, purple and red have to cross over here to find this one. And there we go. So that's the point I'm looking for. Wow, that was super undramatic, right? Bam! That's the point I'm looking for. So with those two covered, again, since I'm using the isosceles trapezoid, and you kind of see it right here, so boom, 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 would be my isosceles trapezoid. This would actually be my parallel line. I missed a bit. Let me move it. Okay. And so again, I'd point out that you should be able to see the isosceles trapezoid construction here. And because I was able to construct an isosceles trapezoid over the top, that's just congruent to this one. If this one is parallel, these should be too, which makes this line parallel to the original. Okay. So complicated, but not terrible. So let's go to the line that's perpendicular through P. You're going to see very similar thinking here. It's all about picking the right one. So I need a structure that is going to be automatically perpendicular. I don't want that. So the one I'm going to pick this time around is going to be a kite. Now the reason I want a kite has nothing to do with the side lengths I'm currently drawing, but has everything to do with the relationship of the two diagonals. So I take this diagonal and this diagonal. I know that's a terribly drawn kite. Please forgive me for that. If I take these two diagonals, by rule in a kite, those have to be perpendicular. So if I'm looking for a perpendicular, oh, there we go. Okay, so I'm looking for a perpendicular line, whatever. Give me a red. Bam. Okay, so if I'm looking through a perpendicular through P, all I really have to do is take this kite and make it on this figure. So just like the one above, the first thing I should probably do is realize what I need. And in this case, I do need 4 points again. 1 point, luckily they gave me, so they totally gave me this point that's in the upper top corner. Again, just like before, I have this line. I just need to define 2 points. Now here's where a lot of people got stuck on the Khan Academy piece because they never define these 2 points. Like it always starts with points. So if you're not taking time in your very first step to identify the points you need to actually construct from, for the love of God, stop doing that. Please define these 2 points first. Because if you were using like a compass, the very first thing you would do is say, I want to start from this point and identify it. So that's what you should be doing here as well. And I can do a little better job, so let me move these. Now, so now I have several points kind of already identified. I have the top point, which is good, and now I have these 2 points, which kind of serve as this guy here and this guy here. Now I need this bottom one. Now, just like before, I know the bottom one has to be kind of in the vicinity of here. Okay, so I don't know exactly where it's going to go, but I can locate it if I use the principles of fixed points. So again, I'm going to need 2 points to fix a point. So what I need to decide is how P was fixed in space and use those same distances but below the line. It's going to come down to circles, guys. You know that. Like by now, this is totally second hat. So what I need to do is realize that if I take a circle from this one anchor point out to P, that should also define where my other point should be down here. It is not defined yet because one distance is not to fix a point. But if I take a second value here and run it through P as well, you'll see that it now gives me an exact intersection point. So the point I'm looking for is actually boom right there. I can do a little better job. Let me grab a normal pen. Bam! Okay, here we go. Bam! Okay, so there's the point I need, the reflected point. And again, if you're looking very carefully, you can see the kite that I'm talking about that I constructed. And this is a line which I'm now going to color in red that I'm looking for. This guy right there. This is going to be my perpendicular one. I don't know why this program has such a tough time with lines. That's going to be a perpendicular line. So again, you're kind of seeing the kite construction right next to the kite, which is why I'm using it. So in the same way you saw the isosceles trapezoid, hopefully now you're seeing the kite. Here's the last one for this section, for this side. I need to bisect, which means cut directly in half using a perpendicular line in this segment. Now luckily they gave us points to start with, but we still have to pick the thing we need. And in this particular case, what you were looking for is an isosceles triangle. Let me tell you why. So an isosceles triangle is the thing we need because there is this property of isosceles triangles that states if this triangle is indeed isosceles, and that means if I take a line from the very, very top and intersect the middle, it should end up being bisected, boom, and it should also end up being perpendicular, which is 100% exactly what we're looking for. So again, it breaks down to identifying points really well. No surprise if that's getting repetitive. It should be. Okay. To define this triangle really well, I'm going to have to pick out 3 points. So I have one here and one here that takes care of the side. I don't have the top middle, and again, it's one of those things where I can't just guess. I don't want to regress back to like because I told you so, because I'm Mr. Collins kind of arguments, which I never did. So I need this point here. So let's go back to this sketch right here and try to identify better what makes this point right here so special. Wow, that turned out larger than I thought. What makes that point so special? What makes it unique? What defines it? What fixes it in space? And hopefully you guys notice that since this isosceles, this side length should be the exact same as this side length. And if these side lengths are the same, lengths are the same, that means circles are the same, which means if I want to find this point in the middle, I'm going to have to use the same size circle from each side. So these have got to be actually the radii. Allow me to demonstrate. So if I take this circle, which I'll color in green, and I run this out. I don't have to necessarily run it out all the way here. I just need to kind of run it out somewhere past the middle. If I take this same circle, okay, and I use the center over here as well, that means if I look at the intersection, I should have my isosceles counterpart. Now the reason that is because if I consider this radii and I consider this radii, those radii actually are the same radii, which means that they're going to be isosceles. Now luckily for me, because of the way this works, I also have radii that go to the bottom intersection point as well, which is why this actually works. So if I have one point of contact on the top, one point of contact on the bottom, lo and behold, I should have my isosceles line. So again, you're seeing the similarities of this isosceles triangle construction with the actual one over here as well. Okay, so getting a little bit tougher, but certainly well within our wheelhouse. Those are some skilled constructions right next to some nice reasoning pieces. And again, I hope you guys kind of caught like why these pieces actually work for our constructions, because it does have like the qualities and the distances we're looking for, and those qualities and distances are all made possible because of circles. So that's the end of what's this, part 4, part 5, I forget, and I will see you guys on the other side of it.